Okay, so today we're going to look at a more formal application of sketching and end behavior. End behavior refers to how the graph ends, like where the arrows are pointing really. We talked a little bit about this last week. We looked at the degree, and that's the highest exponent. Make sure you're looking for the highest exponent because sometimes it might not be in order. And we look at the leading coefficient. Whether it's positive or negative. We look at the degree and whether it's even or odd. So we said when it was even, it looked kind of like a parabola. The arrows point in the same direction. If it was positive, it looks like a positive parabola. The higher the degree, the more bumps there will be in there. And when it was negative, it looked like a negative parabola. So when we talk about formal notation for end behavior, we look at the axis, and we talk about where the arrows are pointing and whether the axis is going to positive or negative infinity. Well, looking at the graph, this side of the graph goes to positive infinity, and this set of x's goes to negative infinity. Goes to negative infinity. And the upper y-axis, the positive y-axis, goes to positive infinity, and the negative y-axis goes to negative infinity. So for this positive even graph, we say that f of x, this is our f of x, our equation, our parabola, our graph, whatever it is, f of x goes to, the arrow means goes to, positive infinity, as the x's, the x-axis here, goes to positive infinity. So on the positive side of the graph, the function is positive. That's what that means. Goes to positive infinity. Then we say f of x also goes to positive infinity. Over here, it's still going to positives as the x's go negative. So as the negatives continue this way, the graph is going to continue to go up. So we say f of x goes to positive infinity as x goes to negative infinity. Now this part is always going to stay the same because you're always talking about what happens on the positive x-axis and what happens on the negative x-axis. What changes is the f of x part. They're both positive, so these both go to positive infinity. So you can really set up your problems to look like this. F of x goes to what as x goes to positive infinity, and f of x goes to what as x goes to negative infinity. And then you're just filling in the blanks. For this problem, my arrows are both pointing to the negatives, so on the positive infinity, my graph is going to negative infinity. And on the negative infinity side, my graph is also going to negative infinity. We know that the parabola and the evens are going to have the same arrows. The directions are in the same go in the same direction. So these are going to be the same if they're even. When it's odd, let's see if I can move this up a little bit. Okay, so when it's odd, it looks like a line. The arrows are in opposite direction. And so let's look at what that might look like here. A positive odd. Oops, let me do it in a different color. Positive odd. Might look like that. And a negative will look like that. So we can say for the odds, and we're going to set it up, f of x goes to what as x goes to positive infinity, and f of x goes to what as x goes to negative infinity. So when we look at this graph, we see positive infinities over here. So let's put that on there, positive infinity, and the graph is going up, so it's going to positive infinity as x goes to positive infinity. And over here, we have negative infinity, and the graph is going down to negative infinity. So we see that we get opposite signs in your f of x part. But again, this part doesn't change because we're talking about the positive side of the x-axis and the negative side of the x-axis, in which direction they're pointing. So let's look at the negative one and how we write that. This is your formal notation. There will be a question like this on the test, but it'll be like multiple choice. You have to pick the correct notation. So again, it's going to look like this every time. Okay, pay attention to which one it actually puts first in a multiple choice type question. But as x goes to positive infinity, we have positive infinity over here, negative infinity, positive infinity. So as we're over here at positive infinity, the graph is going down, so that's negative infinity as x is at positive infinity. And over here where x is at negative infinity, the graph is pointing up, so it's going to positive infinity. And you don't have to put the positive in front of it, you could just put infinity. And again, this part's the same. What you're changing is what the f of x is doing. And with the odds, these are going to be opposite. With the evens, they're going to be the same. Ooh, that's messy. With the evens, they're going to be the same. So this is how you write it, and then to sketch it, we're going to use just the ideas that we were before, but we're going to look at it in already factored form. So to sketch, let's say f of x equals negative x minus 3 squared times x plus 1 times x plus 2. So it's already factored, so we have to identify our zeros, or our x-intercepts. The 0 for this one is going to be positive 3. This one's negative 1, and this one's negative 2. And we have a negative in front, so that makes it negative. So we have zeros of 3. 3 has a square on it. That makes 3 a double root. I'm going to put dr next to it for a double root. And then the other ones are single roots, negative 1 and negative 2. Now, is it odd or even? So it's negative for that negative, and we have x squared. So I have x squared times x, which is x cubed, times x, which is x to the 4th. So if I multiply this out, this would be a negative even, because you would have negative x to the 4th plus blah, 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 blah. The rest of it doesn't matter. You don't actually have to multiply it out. So I have negative even, I have a double root, and we said a double root a double root bounces off the axis. So it looks like this or that. A triple root, I like to say, snakes through. So all odd roots are going to pass through the axis, but the odd exponents that are higher than 1 are going to kind of make this snaking motion as it goes through the points, or it might do it on its way down. And it's called an inflection point because it changes concavity. It changes from concave up. It changes from concave up here to concave down, or concave down to then concave up. So it's actually called an inflection point. Okay, so back to this graph. It's negative, it's even. I have 3 roots, but one's a double root. So I have positive 3, I have negative 1, and I have negative 2. So negative even means down and down. They both open down. So we're going to say the graph looks like this. Let me use blue. Down. I'm going to go through the negative 2 and negative 1. So through negative 2, through negative 1. I'm going to turn around and I'm going to bounce off the 3 and then continue to go down. So there's my end behavior. Both arrows are facing down. And you would write out your answer, f of x. Okay, this is where it says write the formal end behavior notation. F of x goes to negative infinity as x goes to positive infinity. And f of x goes to negative infinity as x goes to negative infinity. So we have both negative infinities in our f of x part. And these are always the positive side of the graph and the negative side of the graph. And that's how we draw it. So it's nice when it's given to you already factored. Make sure you count up the exponents and what the degree is going to be. So let's do another example. Let's do one with the third power root. So let's let this be g of x equals x minus 3. I already used 3. Let's use a different number. X minus 4 cubed times x plus 2 and x minus 6, just to be different. So let's look at our zeros. They're going to be positive 4, which happens to be a triple root because it's to the third power here. So 4 is going to be a triple root. It's going to make that snaking motion. A single root of negative 2 and a single root of positive 6. Now, what is my degree? There's no negative in front here, so this is positive. So there's no negative, so that makes it positive. And my exponents are x cubed times x, so that's x cubed, x to the 4th, x to the 5th. So it's x to the 5th, which makes it odd. And odd positive starts down and ends up. Because remember, it always ends with the sign. So if it's positive, it's going to end positive. If it's negative, it'll end negative. And the odds are opposite. So let's see what that's going to look like graphically. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And we'll do it in blue. So it's going to start down here in the negatives, and it's going to end up here in the positives. I have a root at 6, and a root at 4, and a root at negative 2. Okay, and the positive 4 is our triple root, so it's going to make this motion through it. So I'm going to come up, got to turn around and go through this point in this little snake motion. It's going to turn around and go back through the 6 and end up pointing up. And my formal notation, f of x, goes to, we're looking at this arrow first, positive infinity, as x goes to positive infinity, and f of x, that's this arrow, goes to negative infinity as x goes to negative infinity. So always start with that, or, well, I mean, you don't have to always start. You could actually write them with the negative infinity on top, but you just need to pay attention when you're looking at a multiple choice type question as to which x they're writing first. Okay, that's how it gets graphed. So we've kind of already talked about it. Now this is going to become a little bit more important. Like on the test, you're going to have to draw this pretty accurately. Notice I didn't worry about my y-intercept. I'm just worried about the zeros and which way the arrows are going, and does it pass through these funny points correctly? Like on that one, did it pass through that correctly? If it's a double root, did it bounce? Okay.